Hi folks, welcome to Algebra 2 Common Core. Today we're going to start talking about a new kind of function. In Unit 8, this is lesson number 1, square root functions. So we've had some experience with the square root function as we applied them to transformations, and that's where we're going to begin today. In exercise number 1, we want to consider the function f of x equals the square root of x, and its corresponding function, g of x equals the square root of x plus 3 minus 2. So let's start with the function f of x, and we want to do a graph of this. I'm going to make a table of values. Now, for the square root function, we want to make sure that we are using numbers that it's easy enough to take the square root of so that we can find them on our graph. Not that we can't take the square root of any positive number, we can, but it would be more difficult to find it on the graph. So I'm going to start with when x is 0, the square root of 0 is 0. When x is 1, the square root of 1 is 1. I'm going to skip over 2 and 3 because the square roots of 2 and 3 are both irrational numbers. We could approximate them with decimals, but it's easier to go ahead to the next perfect square, which is 4. So the square root of 4 is 2. And then let's go to 9 just so that we can fit all of these ordered pairs on my graph. The square root of 9 is equal to 3. So I want you to pause the video, plot these points, and come back and check with my graph. So you can see that our square root function looks like this. Make sure you label it f of x. It's actually the upper half of a parabola that faces sideways. Now we want to look at our transformation graph, g of x equals the square root of x plus 3 minus 2. Now in part B it says use your calculator to make a table of values, but what I'd actually like to start with is looking at the transformation because we just finished that chapter. So the x plus 3 tells me that I'm going to take my graph of f of x and I'm going to shift it 3 units to the left. Then because I've got minus 2, that tells me that I'm going to shift this vertically 2 units down. And honestly, I think that's an easier way to do this graph rather than making a table of values or looking at our calculator. So take a few minutes, pause the video, and let's take every point and shift them 3 units to the left and 2 units down. I'm going to use a different color for this graph as well. So I now have the graph of g of x, which is the transformation of the parent function f of x equals the square root of x. In addition, I've also made a table of values showing those new points that I got when I moved my original function 3 units to the left and 2 units down. Now what's important to note on both of these graphs is that the left end has a solid dot and we don't put an arrow on the left end of either of those. That's because my square root function doesn't move at all to the left from that point. On the right end, we are putting arrows because we can see that we can continue to take bigger values of x and find the corresponding outputs. So that's going to then help us when we're looking at the domain and the range for each of these functions. So by examining either the graph or the table of values of the original function f of x equals the square root of x, I see that the domain is going to be in set builder notation x such that x is greater than or equal to 0. Its range is the set of all y's such that y is greater than or equal to 0. Notice that I'm including 0 in both the domain and the range because the function f of x started at the point 0, 0, so 0, 0 is part of the domain and the range. Now when I look at the function g of x, I see that the domain begins at -3. So in set builder notation, x such that x is greater than or equal to -3. And the range is going to be that lowest y value, so y such that y is greater than or equal to -2. Now if you were to go to your graphing calculator and try to input values or look at your table of values before the number -3 on the g of x graph, on my table of values in my calculator I would see an error message telling me that I could not take the square root of a negative number. So let's sum up this information in your notes in the box where it says domain of square root functions. First of all, what we're going to say is that the radicand is just whatever is underneath the square root sign in my square root function. The radicand must be a value that is greater than or equal to 0. So whatever my radicand is, I'm just going to call it a, where a is some function. Actually, you know what? Let's call it the square root of f of x. Whatever that function is, we have to make sure that that function f of x is greater than or equal to 0. So whatever underneath the radical has to be greater than or equal to 0 for now. We're going to see later on in the next unit that it's going to be okay to have some negative values, and we're going to talk about a whole new set of numbers called the complex numbers. For now, let's isolate the radicand to being only greater than or equal to 0. So looking at exercise number 2, I'm given another graph, and I want to know what is the equation for this graph. Well, we're getting pretty good at just identifying transformations. So I'm going to go back to my original parent function on this one. So if I were to plot y equals the square root of x again, looking something like this, that is just my y equals square root of x function. I want to know what have I done to the parent function to get the graph that I've got right here. Well, the first thing I can notice is that I can take my graph and I can reflect it over the x-axis. So if I do a reflection over x, that will affect my equation as well. Once I reflect it over the x-axis, then my graph will look something like this. So the next thing that I'm going to have to do is take that blue graph and shift it. If I count the boxes, we're going to shift it 4 units to the left. Now, technically, these two transformations could be done in either order. I could shift first of all and then do a reflection over the x-axis. One of these transformations does not affect the answer for the other transformation in this case. So let's look for the equation that covers a reflection over the x-axis as well as a shift of 4 units to the left. So take a look at your answers and decide which one you think it is, and when you think you have the right answer, come back and you'll see if I have chosen the same one. I chose choice number 1 because the negative sign in front of the radical shows me that I'm reflecting my radical x function over the x-axis. Underneath the radicand is x plus 4, so that's telling me that the graph is being shifted 4 units to the left. So beginning with the red parent function, I want the equation for the black function to be y equals the negative square root of x plus 4. Now, reading the next paragraph together, if you've got your highlighter, please highlight the important parts of this. Sometimes the domains of square root functions are limited. What's going to limit the domain? It's going to be the fact that the square roots of negative numbers do not exist in the real number system. As I said a minute ago, we will see in our next unit that we can define the square roots of negative numbers, but when we do that, we're going to be introduced to a new type of number. Those new types of numbers are going to be the complex numbers, something that you haven't seen yet before in your math classes. But for this chapter, we are just going to focus on real numbers, so that means that we want to make sure that our radicands are greater than or equal to 0. So in exercise number 3, it says, which of the following values of x does not lie in the domain of the function? So if we want it not to lie in the domain, let's test out each x value and see which one gives us a real answer. So for example, if x is equal to 6, I'm going to say, let's try it out. Y is equal to the square root of 6 minus 5, which of course is the square root of 1, but the square root of 1 is 1. that is a real number, that checks. Try the number 2. Y equals the square root of 2 minus 5. We are seeing that we now have the square root of negative 3. That clearly doesn't check out because right now I don't know how to evaluate the square root of negative 3. Let's make sure that the other two still work. Y equals the square root of 5 minus 5. That's just going to be the square root of 0. And we know that the square root of 0 is 0, so that one checks. When I check for 7, y is equal to the square root of 7 minus 5. Y is equal to the square root of 2. Now don't be thrown by the fact that the square root of 2 is irrational. Irrational numbers are still real numbers. So this still checks. It would be a number that I could find an approximation for. So the one that did not work was x equals 2 is the only one that is not in the domain. Now, it's the only one of these 4 numbers that is not in the domain. There are a lot of numbers that are not in the domain of that function. So if we want to find the domain, let's take a look at exercise number 4, where we're going to set up an inequality to find the domain of each of these radical or square root functions. So in part A, I see that the radicand is x plus 2. So when I'm trying to solve for the domain, I'm going to take that radicand, x plus 2, and I want to set up the inequality that says x plus 2 has to be greater than or equal to 0. This is a nice, easy inequality to solve for, so I'm going to subtract 2 from both sides, and I get that the domain for this square root function is all numbers x greater than or equal to negative 2. I can test it out. Pick a few numbers bigger than negative 2. For example, negative 1. The square root of negative 1 plus 2 gives me the square root of 1, and that is a real number, so I'm A-OK. But if I choose a number smaller than negative 2, so negative 5, for example, the square root of negative 5 plus 2, that gives me a negative number under a radical. So the domain is clearly the set of all numbers x such that x is greater than or equal to negative 2. So we are starting to see that the domains of square root functions are limited by what the radicand is. Let's go to part B. We want to take our radicand for x plus 12, and we want to make sure that that's going to be greater than or equal to 0. Subtracting 12 from both sides, I'm getting 4x is greater than or equal to negative 12. Dividing by 4, x is greater than or equal to negative 3 would be the domain for this radical function. Let's try part C, 8 minus 2x. That's the radicand. We want to make sure that it's greater than or equal to 0. So I get negative 2x is greater than or equal to negative 8. Dividing both sides of the inequality by negative 2, and remembering that when I'm dividing an inequality by a negative, I have to reverse my inequality sign, I get that the domain for this one is x is less than or equal to 4. Notice that that inequality goes the other direction. I'm picking a number, and the domain is all numbers smaller than that one. Think about why that radical function has a different format for its domain. Now in exercise number 5, we still have a square root function, but this time our square root function does not have a radicand that is linear. By linear, I mean that the variable is just to the first power. In this example, instead, we see that the radicand has an x squared. So it has a quadratic radicand. I'm going to label that so that we have that in our notes to look back at. So when I have quadratic radicands, I'm going to have to deal with them a little bit differently when I'm talking about finding the domain. So the first thing says, let's go ahead and graph this on our graphing calculator. So please pause the video. You don't need to make a table of values for this, but I want you to make an accurate sketch of the graph after you put it onto your calculator. When you're done making that graph, then please come back and check your graph with mine. Please make sure that you do the graphing rather than just waiting to see what my graph looks like. On your graph, you should have been able to see that this square root function actually has two branches. One branch touches the x-axis at -6. The other branch touches the x-axis at +2. We'll be able to algebraically see where those two numbers come from in Part B. So in Part B it says set up and solve a quadratic inequality that will give us the domain for f of x. So we're still going to say, let's take our radicand, x squared plus 4x minus 12, and let's make sure that that radicand is greater than or equal to 0. So we notice here that what I have is a quadratic inequality. We covered solving quadratic inequalities 2 units ago, so this is really good practice before our midterm exam. So the first step is going to be to take this quadratic and set it equal to 0. This quadratic happens to be factorable, so look for your add, multiply. So I've got x times x. I want to add to get 4 and multiply to get -12. So that gives me x plus 6 and x minus 2 equals 0. Factoring quadratics like this should be pretty easy for us by now. Since I'm setting each equal to 0, I'm going to make my t-bar, and I get the two solutions, x equals -6 and x equals +2. Oh, that's where those numbers are coming from. So here's my -6 where one branch touches the x-axis. Here's the number 2 where the other branch touches the x-axis. Now to figure out which part of the real number line is part of my domain, remember how with quadratic inequalities we always set up a number line. And we say let's put those two numbers, -6 and 2. Now since I wanted greater than or equal to 0, that means that I'm going to shade both of those points. Both of those points are going to be solutions for our quadratic inequality. You'll recall that we picked a number in each interval. So for example, I'm going to pick the number -7. It would fall back here before -6. I substituted -7 in here, so -7 plus 6, that's negative. -7 minus 2, that's negative. A negative times a negative gives me a positive answer for the product. Because I'm looking for greater than or equal to 0, I'm looking for any section that's going to give me positive results. So that means I'm going to shade that part. Now let's pick a number that's between -6 and 2, for example 0. That's the easiest one to pick. 0 plus 6, positive. 0 minus 2, negative. Positive times negative tells me that I've got a negative result. I don't want negative, so I'm not going to color that part in. Instead, let's look for a number bigger than 2. How about 4? When I test it in here, 4 plus 6, positive. 4 minus 2, positive. So my product is positive, and we're going to color that part in as well. So from this number line, we can then write down that the domain for this quadratic radical function is all the numbers x such that x is less than or equal to -6 or x is greater than or equal to 2. If I try any numbers between -6 and 2, I see that it's going to give me an error. You can also look on your graphing calculator and see that on the table of values. Let's try exercise number 6 together, where we again want to take a look at this square root function. F of x this time is equal to the square root of x squared minus x minus 20. We want to algebraically solve for the domain. So for this domain, we are going to make the radicand x squared minus x minus 20 greater than or equal to 0. I'm going to jump right away to my factoring step. So I see that this factors into x minus 5 times x plus 4, and I'm going to set it equal to 0 to solve for those numbers on my number line. That's going to give me x equals 5, and x equals -4. So we make the number line, putting those two numbers, -4 and 5. Both of those numbers are part of my domain, so I'm going to fill in the circles at -4 and 5, and then test numbers in each interval. So for example, let's test the number back here, -5. Substituting -5 in here, I get a negative number. Substituting -5 in for x here, I get a negative number as well. So negative times negative is positive. And that's exactly what we want. We want to end up with a positive product. So let's color in that section of my number line. Now when I test a number between -4 and 5, for example, the number 1. 1 minus 5, that's negative. 1 plus 4, that's positive. Negative times positive is negative, and that's not the kind of product I want, so I'm not going to color that part in. Pick a number in this interval, for example, 6. 6 minus 5 is positive. 6 plus 4 is positive. Positive times positive is positive. So I am going to color that section because it gave me a positive product. So we can then read our domain right from that number line. So the domain is going to be the set of all numbers x such that x is less than or equal to -4, or x is greater than or equal to 5. Now I would encourage you to take out your graphing calculator and type this into y1 and see if your graph has two branches where one branch goes up to the x-axis at -4, touches it and stops. The other branch starts at the number 5 and then goes ahead on the right side. But notice that there's no numbers graphed between -4 and 5. Now I'd like you to pause the video and take a few minutes to do the 2U triads. When you're done, come back and check your solutions with mine. Welcome back. Take a look at the U-triad example answers. So number 1, I got that the domain is x such that x is greater than or equal to 1/2. This was just a linear function underneath the square root, so that's why I don't have to do a lot of testing. I just have to solve that inequality. For number 2, I see that I've got a quadratic underneath the radical, so I set up the quadratic inequality, x squared minus 2x minus 8 is greater than or equal to 0. I factored it, I found the numbers on my number line, and then I tested a number in each interval to see which intervals worked. The two intervals that worked were the domain, the set of all x such that x is less than or equal to -2, or x is greater than or equal to 4. If you have any questions about graphing radical functions or finding the domains of these radical functions, please come and see me during activity period because we'll be working with these during our next class. Thanks, have a great night.